Okay, at this point in my planning, it started to maybe occur to me that perhaps you weren't as comfortable finding vertical asymptotes as I thought you were. So let's make sure that we can find the vertical asymptotes for all of these. We have y equals 1 over 2 parentheses x plus 1. Does that have a vertical asymptote?
Yes.
Where?
-1.
At x equals -1. So, do y'all understand it's a vertical asymptote if the denominator equals 0 but the numerator does not?
Yeah.
Okay, that's most of the time. And with rational functions, that's always true. If the denominator equals 0 but the numerator does not, it's a vertical asymptote. So let's talk for a second about everything we know about vertical asymptotes. We know that the limit doesn't exist there as it approaches that number, right? But that it can either be positive or negative infinity. You know, we can talk about it that way as well. What do we know about its continuity at a vertical asymptote? Can it ever be continuous at a vertical asymptote?
No.
No, because it's always a non-removable discontinuity there, right? Okay. Let's talk about g of x equals x plus 1 over x squared minus 1. If we factor that, we can see that there are two restrictions. There is a restriction at x equals -1 and at x equals +1. Both of those are discontinuities, but only one of those is a vertical asymptote. Which one?
X minus.
X equals -1.
X equals +1 is a vertical asymptote. The other one is a whole, right?
Right.
Yes. So we say there is a vertical asymptote at x equals +1. If I asked you to find the whole, would you know how to do that? Where's the whole? At -1 comma what?
0.
How would you find the whole? Plug in -1 after you have removed the whole. So if I plug in -1 here, what do I get? -1/2, yeah. That's how you find the whole. Isn't that interesting?
Sure.
So let me ask you this. What is the limit as x approaches -1? Very good. It's the y value of the whole. Last one, let's talk about h of x equals cotangent of x. We talked about sine of x in terms of continuity last time, right, you guys? And we said that it's continuous everywhere because it has no vertical asymptotes, but sine and cosine are continuous everywhere. But the other four have vertical asymptotes. So let's talk about where the vertical asymptotes are and how to find them. Cotangent of x is the same as, split him up,
Cosine over sine.
cosine over sine. So if I look at it that way, it's going to have vertical asymptotes anywhere the denominator equals 0. So that would be at sine of x would have to equal 0. And where is sine 0? Where does that happen? In radians. It has to be quadrantal.
Pi over 2.
I think sine is 1 at pi over 2.
Just kidding. And it would be just pi.
0 and pi? Yeah? Okay. So we would say it's at 0, pi, 2 pi, 3 pi, 4 pi. How long could this go on? Forever. Is it also true at negative pi? Negative 2 pi? Negative 3 pi? So basically, it has vertical asymptotes at every integer of pi. Make sense? So we say it this way. We say x equals k pi, where k is any integer. So that's where your vertical asymptotes are for cotangent. Right. Let's take a look at the limit as x approaches 0 of 1 plus 1 over x squared. What's 0 doing there? Hey guys, what's up? 0 in that problem. 1 plus 1 over x squared.
It's being approached.
It's being, okay, just tell me, what is it? It's obviously a restriction. Is it a whole or an asymptote? It's a vertical asymptote. So we're talking about the limit as we approach a vertical asymptote. And we know there are only three options for that. Infinity, negative infinity, or just plain old does not exist.
Correct.
Our only job is to figure out which. And we can usually do that by just investigating the graph when it's at a vertical asymptote. So it turns out in this particular problem, if we graph it, there is a vertical asymptote at 0 right here. And there is a horizontal asymptote, oddly enough, not at 0, but at 1. It's hard to see, like algebraically, but if you get a common denominator here, you can see the horizontal asymptote much better. If I get a common denominator, that's what it looks like, right, you guys? And you can see that the horizontal asymptote is at 1.
Yes.
Okay. So all we need to know is, where does the graph live? So if I plug in -1, I get what?
2.
Very good. I get 2. So it lives up in this area here, approaching positive infinity from that side. And then if I plug in +1, I still get 2. So it lives up in this area. So what can we say about the limit as x approaches 0? It equals positive infinity, right, you guys?
Right.
Makes sense?
Yes.
No problems? We're all pretty comfortable with that? Yes? Okay. Let's talk about the limit as x approaches 0 from the right of 3 cotangent of x. Cotangent of x. We just talked about this, right? So that's why I decided to do it on the very next slide, because you would still remember
3 cosine of x.
that that's the same as cosine of x over sine of x. And we already know, because we did it on the previous slide, that 0 is a vertical asymptote there, correct? So all I need to know, really, is whether it's going to what? Positive or negative infinity there. What would be a way I could find out? You could put it in your calculator and look at it and see what's happening as you get really close to 0 from the right hand side, right? So let's pause right there and let everybody put that in their calculator. So we can see from our graph that right here to the right of 0, it looks like this. So what do we say about the limit as x approaches 0 from the right? It equals positive infinity. Great. So that's a good kind of breaking point to stop there, because after this we'll talk about limits at infinity.